week, we are talking more about the circuit design, and we'll cover some topologies, 4 different topologies that deploy the feedback. And the first topology is voltage feedback. So voltage feedback means at the input of the feed forward amplifier, we have a voltage V1, and at the output, we get the output voltage and we feed it back to the feedback structure K. So as you can see, input is voltage and output is voltage. That's called voltage feedback. And if you look at the formula, as you can see, input is V in, and this V1 is V in minus feedback output, VF. And we also write the feed forward, which is output is A0 times V1. And combining these two, actually these three, VF is K times V out. And combining these three, we write the formula and we get the closed loop gain. Now this is closed loop because we have a feedback structure. The closed loop gain is A0 divided by 1 plus KA0. What is the open loop gain of this amplifier? It's A0, right? So from A0, we now have the gain instead of A0, we have the gain A0 divided by 1 plus KA0. Well, instead of K, sometimes we use the beta. It's the same thing, feedback factor, okay? So as you can see, we drop the gain with the amount of 1 plus KA0. And last week, I explained why we have to drop the gain. Why is it beneficial? Can you tell me why is it beneficial to apply the feedback? There are 3 reasons.
We can increase the bandwidth.
Perfect. One of them is boosting bandwidth.
And we don't want huge change to output. That's why we don't want huge A0.
Perfect. We call this insensitivity. Maybe a few more. Şu inputumuz olsun. V in. And let's say this is your V out.
We can change our input and output resistance.
Evet. R in ve R out'u değiştirebiliriz. Feedback uygulayarak.
And we can increase the linearity, right?
Yes, that's also one of the most important ones. So if a circuit has a structure like this, it's not linear. We prefer to have a linear structure rather than this one, like a perfect relationship between V out and V in. Okay, because a non-linear system like this will distort your input. If you have an input like this, you prefer your output to be like this, right? But in this case, that might not be the case because the response to this input here will be different to the response here, right? In this one, the response is same. The slope is the gain. Here, the gain is slope of here, the slope of here. So small signals will have a big gain, right? And big signals will have a smaller gain in the nonlinear case. So basically your output will be distorted and we don't want that. And providing a feedback boosts the linearity, transform from this to this, okay? We lose the gain, but we accept that penalty to boost all these things. So back to circuit design, as you can see, the gain drop, but it comes with many advantages, as I mentioned, okay? So for instance, this is a circuit structure of that topology, voltage feedback. We have an input voltage, and at the output, we have the output voltage. And as you can see, we have the output with this feedback R1, R2. We get the feedback, apply it back, and then basically we have a closed loop. The amplifier itself is A0, and this feedback structure is K. So you get the voltage V out, you sense the voltage through this feedback structure and get the output VF and basically feed it back to this structure. Well, this structure is a difference amplifier or differential amplifier. So basically V in is V1 and this feedback structure is V2. That's how you apply the feedback. For instance, if you want to solve the gain of the circuit, well, gain is GM times RO and parallel ROP if there is no feedback. Basically, this GM is multiplied. The small signal current is current mirrored here. This is called diode connected differential amplifier. So the gain here, if there is no feedback, is here, okay? And this is your A0. This is your open loop gain. We are trying to find closed loop gain, right? So what you do is A0 divided by 1 plus KA0. Well, the thing that you don't know here is K. Well, what's K? You can find it, right? K is the gain from output of the feedback to the input of the feedback? Well, your output of your feedback is here. Input of the feedback is here. So basically the transfer function from output to the input of the feedback is your K, output, input. And in this case, it's a simple resistive division, R2 divided by R1 plus R2. Okay. So going, as you can see, this is the A0 at the numerator, and at the denominator, we have 1 plus K times A0. Okay? And if the A0 is big, this will be 1 divided by K. 301'dan hatırlarsanız non-inverting, inverting amplifier'ı işlerken bunun üzerinden geçmiştik biraz op-amp'larda. 1 over K orada 1 over beta'ydı. Aynı şey. Okay. How about input impedance? How can we calculate the new input impedance? So this is how we model it. We connect the input source, and this is the current. And because this feedback structure providing voltage, we assuming the current is same. And this is the input impedance of this amplifier. And as you can see, I in times R in is the voltage here. This current times this impedance, assuming that this one is ideal. So we bring the non-ideality to the outside. So that's the voltage in this node, which is V in minus Vf. Okay. So writing this feedback voltage as output times K, and then rewriting the impedance V in over I in. As you can see, the input impedance boosted by the same factor, 1 plus Ka0. Okay. And if this is an example, you can look at it later. How about output impedance? Well, output impedance is just like finding Thevenin resistance. You connect the test source, you find the test currents, but of course you kill the independent sources. There was an input here, so we kill it, okay? And then you just find Vx over Ix. And in this case, doing the calculations, Vx minus this voltage, which is here, K times Vx is here, K times Vx, and you multiply with minus because you're subtracting it here. That's minus times A0 is the voltage here. So subtracting Vx voltage minus that voltage divided by R out gives you this current here. So it's saying that the current by the feedback network is neglected. So we are assuming that the input impedance of this feedback network is huge. Okay? So basically this impedance is big, R1 plus R2. So in that case, this Ix will be equal to this current. So you can write this. Well, as you can see, the output impedance now dropped by the 1 plus Ka0. Okay? So for a voltage amplifier, basically for a regular amplifier, this is called voltage amplifier. The feedback boosts the R in, but it decreases the R out and decreases the gain by the same factor. What's the factor? 1 plus Ka0. Okay? So your input impedance boost multiplied with this is your new input impedance. Your output impedance or gain is divided by it. Okay? Compare this. These are like without feedback, and this is the factors is with feedback. Okay. So as you can see, every amplifier will have a characteristic. This is different for different amplifiers. This is for voltage. So for instance, now let's look at voltage currents. How does it work? Well, voltage currents means you have voltage output. Well, this is voltage current feedback. So basically voltage feedback is voltage amplifier. Voltage current feedback is at the output you have the voltage, at the input you have the current. Okay? So this will also give you the idea of your main amplifier. Why? Well, if you are getting the output, if your feedback system is getting the output, well, that means you have a V here. And if your feedback system is giving input the current, well, that means your input is the current. So your amplifier is a input current, output voltage amplifier. This is called trans impedance. Why? Output is V, input is I. That's called Z. So it's called trans impedance. Okay. So feedback structure takes the voltage and provides currents. Okay. So it's opposite of the main amplifier. This is the main amplifier. This is the feedback. So any questions so far? All right. So I'll continue with this voltage currents, but with the following voltage feedback. It's good to explain how actually cell phones work. So in 301, you learned diode circuits, right? You learned how we provide constant voltages with Zener diodes, right? And we learned what's a regulator. Actually, when you use a cell phone, you have a battery that's called rechargeable battery, and you are running all the integrated electronics inside the phone with this battery connected here. So when this battery dies, or let's say it drops from like 10 volts to 9 volts, 8 volts, this VCC, when it drops, well, your circuit will get affected, right? So you need stable voltages here. So that's called LDO, low dropout outputs. So basically you have a battery, the output is connected to a circuit that will give you a stable voltage. For instance, this is a regulator. The battery is driving the circuit, for instance, but you have a Zener diode here, which provides a constant voltage. And connecting this amplifier and running this feedback, we make sure that this Vref is equal to this Vref, which is constant, so that this voltage is constant due to resistive division. So this constant voltage actually runs your cell phone, which is called regulated supply voltage. Well, this is the most simple way of creating a voltage regulator. There are like much more complicated ones. But what I'm saying is, as we discussed a few minutes ago, feedback provides stability. So instead of something dropping, we use that to fix that voltage to a reference voltage, right? There are a lot of different applications of feedback. So one of them is this one. So going back to the voltage current feedback structure, we already explained how it works. It takes the voltage, sends the voltage, and then the feedback structure. I'm talking about feedback structure. It sends the voltage, provides current, and then these currents are summed up, and the input of this main amplifier is current, and the output is voltage. Okay. So similar calculations to the other amplifiers. Just you have to just look at the circuits and put your math skills. Your V out is multiplied with K, becomes your IF, right? This one. So I in minus IF is this current. If you multiply with RO, so instead of A0, now we have the term RO, okay? Because A0 was voltage divided by voltage. Now we have voltage divided by current. So instead of A0, it's using RO, okay? So it's multiplied with RO, and that gives you your out, right? And then just applying this, you have the V out over V in, R out divided by 1 plus K R0. Similar to the voltage, your gain again dropped by the same factor, okay? Let's look at the input impedance. So probably you can do the circuits yourself in the Razavi. Or actually I'll solve it. But jumping to the input impedance. So this is your input. So we have a Vx as the input voltage. We're trying to find Vx over Ix. Okay. So the IF current is K times Vx over Rin times RO. What does it mean? Well, the voltage, basically Vx is here. You multiply that, you divide that by Rin. You multiply with RO. You again multiply with K. So this is your current IF. Okay? And putting that into the KCL, this current minus that current gives you this current. So rewriting it, Vx over Ix is this. And as you can see, different than the voltage amplifiers, now your Rin impedance is not boosted up. Your Rin impedance is actually boosted down, right? Well, is it a good thing or bad thing?
Can you repeat the question?
Voltage amplifier'da Rin boosted olmuştu. Değil mi?
Hı.
Bir ideal op-amp'ın Rin'i ne olması isteriz?
Sonsuz, infinite.
Sonsuz. Dolayısıyla mantıklı. Feedback Rin'i boosted ediyor ve Rin'i büyütüyor. Bunun olmasının mantığını bir input bağladığımız zaman iç source rezistansı vardır her zaman. Ne olacak? Şuradaki voltage'ınız maksimum burada gözükecek. Çünkü this input impedance is big. Resistive division. This input, we wanted to show all of them here. This is voltage amplifier. So feedback actually works for our purpose. Output impedansı da ne oluyor? Küçültüyoruz. O da mantıklı. O da bizim için iyi. Now we are looking at other amplifier, which is transimpedance amplifier. The input is current, the output is volt. Yeni bu devrede input impedansını scaled down. Rin divided by same factor. 1 plus K R0. So Rin'in küçülmüş olması bu devrede iyi bir şey mi, kötü bir şey mi?
İyi bir şey gibi. Çünkü inputumuz current.
Aynen öyle. Because the current is the input. We want all this current go here, right? And the way that all this current can go here is this impedance is small. So actually we want in this amplifier type, we want Rin to be small, right? So this feedback sensing the voltage and deploying currents back to the output basically helps our purpose. Okay. So feedback always helps our purpose. Just I am showing you how. Okay. So output impedance'a bakalım. Bu devrede output impedansın aynı voltage gibi olmasını bekleriz. Yoksa tam tersi davranması. Yani mesela compared to VV, IV amplifier, the Rin drop.
The same. Our out should be the same because our output is still voltage.
Exactly. So we want still our out to be big, right? So why? Because as we look at the output impedance here, kötü çizdim, şöyle çizeyim. You get a voltage here because of the GM, and this voltage, you want it maximum to be here. So you want minimum drop here, right? So you want your R-out impedance, So you want your R-out impedance to be still small, right? So in the VV, impedance was dropping R-out. And in the IV case, IV amplifiers, you still want your R-out to be dropped. Let's check if feedback does that. Well, actually, it does that. Şöyle kaydırsam. Okay. So as you can see at the bottom, gene yazıyoruz. Output impedance'a nasıl bakıyorduk? You can kill the independent source. There's a current source. Killing means you open it. Okay, so you kill it. This is the circuit. We need to find Vx over Ix. So this called Va, and you write Va as K Vx R out minus. So Vx minus that divided by R out. Şu akımı buluyoruz. Şuradaki akımı sıfır çok küçük olduğunu düşünüyoruz. Bunu load etmediğini düşünüyoruz. Is our assumption. So then you can see that your Vx over Ix is actually dropped by that same factor. 1 plus K RO. Okay? Which is good. Dolayısıyla bunu generalize olarak şöyle özetleyebiliriz. There are 4 different amplifiers. VV, IV, VI, II. Okay? These are the main amplifier type. I'm talking about these ones. So input is V, output is V. In this case, input is I, output is V, and so on. When we look at the feedback structures, well, feedback structure should be, can you tell me how should be the feedback structure? Mesela VV'de inputunuz V, outputunuz V. Feedback structure'ın input'u ne olur?
Voltage.
Voltage. Çünkü output'tan alıyorsunuz. Input'u ne olması lazım?
O da voltage.
O da voltage. Okay. How about IV case? Your main feed forward amplifier is IV. How should be your feedback?
Voltage input. Voltage current.
Voltage, current. How about this?
Current voltage.
And this one?
Current.
Okay. So as you can see, it's opposite. I mean, not opposite, but if it is voltage, logically your feedback wants to take the voltage and deploy voltage back.
Hocam, yani I saw it, you tell it, but how can I get voltage and provide current? There was 2 golden rules and there is no current going to the op-amp, but still...
Tamam, hemen işte örnek yapalım. Mesela şurada.
Ya yaptık aslında. Hani matematiğini de anladım ama böyle genelde ben devreleri kafamda canlandırabiliyorum. Bu çok zor oluyor.
Yani soru çözmeniz gerekiyor. Mesela this question. This is an amplifier, and as you can see, feedback, this is your input current, this is your output voltage, IV, değil mi? Your feedback circuit takes this voltage, and there is some resistance connection between the input and voltage, so this is your feedback structure. Takes the voltage, transform current. Voltage'ı aldı, input current'la voltajı birleştiremezsiniz. Tabii ki akıma dönüştürecek. Dolayısıyla buradaki feedback circuit'ın output'u voltaj olamaz zaten. Çünkü inputunuz akım. Dolayısıyla ancak akımla akımı toplayabilirsiniz. Akımla voltajı toplayamaz. Dolayısıyla bu feedback network'in output'unu akım olarak yazmanız gerekiyor. Çünkü devrenizin input'u akım. Okay? So this is really important. So basically, let me take a screenshot. Quite messy, but this is important. Learn this thing well. Burada daha sonra şunlara bakacağız. Mesela bu devrenin open loop gain'i nedir? Veya closed loop gain'i nedir? Hani biraz şimdi şu örneği çözelim mesela. Burayı anlamayan var mı arkadaşlar? Varsa lütfen sorun. Geçen 2-3 ders önce ne konuşmuştuk ya?
Haklısınız hocam. Yani benim sorum yok. Teşekkür ederim.
Okay.
Benim de yok hocam.
Benim de yok hocam.
Tamam, süper. All right. So, Ahmet, do you have any questions?
No hocam.
Okay, perfect. So, long story short, whatever your main feed forward or main amplifier, your feedback network should act correspondingly. If your output is voltage, that's the input of your feedback. Okay. If your output is current, that's the input of your feedback. And your output of your feedback should be input of your feed forward. Okay. Zaten feedback de bu demek. Okay. So, şu örneği çözelim. So, this is a current voltage amplifier, as you can see. Input is current, output is voltage. And asking, prove that feedback is negative in part A. In part B, asking the open loop gain. And in part C, asking to calculate the closed loop gain. So first, let's look at how the feedback is negative. We should follow the signals. If input I increases, şöyle bir şey increase ediyorsa bu ne oluyordur? If this current is increasing, what is this current doing?
Also increasing?
Well, opposite directions, right? If this current is increasing, this one, I in, şu 20 olsun, şu I'in de 15 olsun. Buraya 3 ekledik, 18 oldu. Bu akım ne olur? Yani şey olur. Efendim?
Hani ikisi aynı not, giren çıkan toplam 0 olması gerekiyor gibi geliyor bana ama.
Ama tabii şöyle bakacaksınız conceptually. Bu tarafa giden akım artı olarak, delta olarak artıyorsa şu tarafa giden akım ne olur?
Dengelemek için azalıyor mu?
Yani ikisi aynı not zaten değil mi? Yani bu taraf bu 10'dan eksi 10'a düşerse şu nedir? Eksi 10'dan 10'a çıkıyor demektir değil mi?
Evet, şimdi anladım.
Okay, they are opposite polarity. So if this current increases, this current, since it's the same on the transistor, because this current is your efendim.
Hocam, current source sabit olduğu için mi bu akım artması azalması karşılıklı oluyor? Fix bir current source kullandığım.
Current source'dan bağımsız olarak şuradaki ayın bir sinusoid sinyal oldu. Tamam. Şöyle arttı. Şu sinyal ne olur? Tam tersi opposite polarity olduğu için düşer. Yani şu verdiğim örnek 10'dan eksi 10'a düştü. Bu ne demek? Yani bu hani circuit 201. Hani tam tersi. Bu current 10'sa bu current eksi 10'dur. Tamam. Dolayısıyla bu düşerse bu çıkıyor demektir. Eksi 10'dan 10'a çıkıyor demektir. Think very simple, Nejat. I mean, it's not really complicated. It's just simple. If this, kaldıraç gibi de düşünebiliriz. If this is decreasing, this is increasing, right? Yani burada polarity önemli olan. Şuradaki akım aynı akım. Sadece notation'dan bahsediyorum. Okay. Şu 10'sa, şu eksi 10'sa, şu 10'dur. Eksi 10 akım demek, buraya gidiyor demek. 10'la, değil mi? Dolayısıyla if this current is decreasing, that means this current is increasing. If this current is increasing, input is increasing, that means this current is decreasing. Current düşerse, şuradaki voltaj large signal düşünüyorum. Bu current ID1 düşerse, buradaki voltaj yükselir. Çünkü şurası sabit voltaj, değil mi? Sabit voltaj çarpı düşük current çarpı rezistans daha büyük bir voltaj. Okay? Because this voltage is constant. If this current is decreasing, this means the voltage here is increasing. If the voltage here is increasing, o zaman ne olur? Buradaki voltaj arttığı için buradaki akım da artıyor. O zaman şuradaki not düşüyor. Buradaki not düşerse şuradaki V out over RF çoğu buradan gidiyor. RF'in büyük olduğunu düşünürsek 1 bölü GM'e göre. V out bölü RF artı 1 bölü GM şu akım. V out düşerse 1 bölü GM'e göre RF'i büyük diyelim. Buradaki akım da düşer. So this is decreasing. So as you can see, when we have an input increasing, this input current would want to increase, but you are getting a negative correspondence. It's in correspondence to that action. This feedback structure is taking a reaction and it's decreasing this current. So this current is not really increasing much because your feedback structure decreased this current. Okay? That's why it's called negative feedback. Eğer siz bu akımı arttırdığınız zaman bu akım da artsaydı o zaman pozitif feedback olurdu. Ve ne olurdu? Sistem osilasyona girerdi. Hatta belki de patlar yanardı. Neden? Çünkü arttırıyorsunuz. Bu da arttı. Tekrar arttı, tekrar arttı. En sonunda ne oluyor? Osilasyon yani dump over'dan yükseliyor ve patlıyor. Değil mi? Yani that's called positive feedback. So we have to use negative feedback. And that's the proof why it's negative. Okay. Any questions? Ben de ilk öğrendiğimde anlamakta zorlanmıştım. Anlamamanız çok doğal. O yüzden bunu tekrar okuyun bence. Anlamazsanız sorun. Çünkü fundamental, bunu bilmeniz gerekiyor. Sadece elektronik sistemlerde değil, genel olarak enerjide de, kontrolde de, sinyalde de bir negative feedback nedir? Nasıl çalışır? It's quite fundamental. You gotta learn how feedback is negative. What does it mean? Okay. So the second part is open loop gain. An open loop gain means without the feedback, what is the gain? Well, as you can see, we close the feedback, we turn it off. Your input, your out. That's it. That's your open loop gain. And input is I in. So the voltage here becomes I in times RD. That's the voltage. Then the current here becomes GM times that voltage. And then you multiply with RD2 is the voltage here. You need to divide it to the currents, to the input. Inputs cancel, and you get your open loop gain, GM, RD1, RD2. Why is it minus? Because this currents here at the output is multiplied with minus GM, right? Small signal, GM is here, RD2 here. So this V in is this one, Vx. So basically this is GM Vx. You got to take the minus of it, right? That's why it's minus. So here is Vx. I'm sorry. Here is Vx. You multiply with GM, put negative, becomes this current, multiply with RD2, becomes this volt. Well, it's basic stuff that you learned in the previous weeks already, okay? Now, when we want to calculate the closed loop gain, well, we need to either solve the circuit, or you can just look at the amplifier type. Hey, this is a current voltage amplifier. And when we deploy the feedback circuit, the Rin becomes boosted down, right? So, and if Rin is boosted down by that factor, 1 plus Ka0. Rin'e bakmıyorduk. Gain'e bakıyorduk, pardon. Gain ne oluyordu? Gain ne oluyordu? Hemen bakalım. Okay. Gain de aynı faktörde düşüyor. 1 bölü KR0 kadar. Dolayısıyla şunu sileyim de. Alright. So A0, gain is becoming A0 times 1 plus. Burada bir A0 divided. Gain düşüyor tabii ki. Feedback düşürüyor gain'i. Niye Rin diye düşüyor? A0 divided by 1 plus KA0. Okay. Bakıyoruz. Closed loop'ta. This is A0, 1 plus KA0. What is K? K is this feedback factor, minus 1 over RF. Why is minus 1 over RF? Because you take the V out, and you provide a current. And this current is basically becomes this voltage divided by this resistance. Because as we mentioned, this 1 over GM is small. Şuradan baktığınız zaman gördüğünüz impedans 1 over GM. Ne impedans o? This impedance. 1 over GM is small. That's why the entire voltage divided by this resistance gives you this current, which is IRF. Okay, so that's your K. Putting into the equation without really solving the circuit in details, just solving the feedback factor and the A0, you can solve the closed loop gain. Var mı sorunuz?
Benim yok hocam.
Okay, süper. There are other networks, so we studied 2 of them. Right? So there is current voltage feedback, which I didn't really get into the details, but you get the current and feedback output is voltage. So of course, this amplifier is a volt current amplifier. And what is a voltage current amplifier? Anybody knows what is it called? Or anybody has a guess? Well, the previous one was called transimpedance amplifier.
Transconductance.
Aynen öyle. And this one is called transconductance. And this GM is, as you can see, similar to the small GM, right? GM V in a transistor was current, right? That's why they use a big GM to define as a good symbol. It's called transconductance. Okay? Burada detaylara girmiyorum çünkü yine aynı mantık izliyor. You just put the current and voltage into the equations. So as you can see, the gain drops again by the feedback factor. This is a good question, which is a practical application. And then it calculates input resistance. Input resistance is boosted. Well, do we expect it to be boosted, or would it be expected otherwise? Looking at the amplifier here, this input of this overall structure is boosted. Does it make sense with the feedback? It makes sense, right? Because this is a voltage amplifier. Input is voltage. So we want this amplifier resistance, input resistance to be big, right? Because this is the input. We want the biggest voltage here. So we want this impedance to be big. Dolayısıyla amplifier'larda şuna bakıyorsunuz. Input'unuz voltage mı? Voltage'sa Rin boosted. Ne kadar boosted? 1 artı K A0 kadar. Output'unuza bakıyorsunuz. Output'unuz voltage mı, current mı? Eğer voltage'sa Rout will want to drop with feedback. Current'sa Rout will want to increase. Okay? Yani aslında ezberlemenize de gerek yok. Şuradaki input'un voltage mı, current mı olduğuna göre feedback bunları ona göre güzel bir şekilde boosted veya tam tersi dropping yapıyor. Okay? Okay. So one other amplifier is the last one, current. And the current one, input is current, output is current. Therefore, feedback structure is also input is current, output is current. And again, it does bunch of equations, simple equations. Gain always drop on all of the amplifiers. Gain is dropping by this factor. Hemen hiç formüllere bakmadan şuradaki Rin'in feedback'le artmasını mı bekleriz, azalmasını mı?
Azalmasını.
Azalmasını bekleriz. Neden? Çünkü this amplifier will want maximum current. Nasıl maximum current alır? Input impedansı çok küçükse, hatta sıfırsa. Tamam. So Rin will take the maximum current. This amplifier will take the maximum current. Only this impedance is small. Therefore, feedback will do that. It will scale down Rin. How about Rout?
It's also scale down.
Voltage ise output'un.
Ama bu current
Voltage ise output ne olur? Scale down olur. Değil mi?
hocam voltage'sa doğru.
Değil mi? Voltage amplifier neydi? Rin büyük, Rout küçük. Neden? Çünkü şurada maksimum şu Rout şu. Şurada maksimum voltaj istiyoruz. Dolayısıyla şurada drop istemiyoruz. Burada current nasıl düşünebilirsiniz? Şu current'ın maksimum olmasını istiyoruz. Dolayısıyla şuradaki Rout'ta büyük olsun ki şöyle çizeyim output'u. This is your GM-VGS. This is your input voltage. So V1, this is your output. Şu output'u şöyle çizdim. Şöyleydi. Bunu Twain'inden Norton'a çevirdim. Şurayı şöyle yaptım. Dolayısıyla bu Rout şu anda paralel. Bu Rout'un küçük olmasını mı isteriz, büyük olmasını mı isteriz? Şuradaki current maksimum olması için. Büyük olmasını isteriz değil mi? Infinite olmasını isteriz ki bütün akım buraya gitsin. Okay? That's why Rout goes high. Okay, make sense? Okay. This is kind of summarized here. Let me refresh this one. 1 second. Saat 6:30 olmuş. 4:30. Okay. So last week we basically discussed system level, and this week we are discussing more circuit level. I will upload the videos, and as you can see, I kind of put the summary here of 4 amplifiers and corresponding circuits. So series shunt. Series shunt means why this is series shunt. I can explain that as well. Shunt series, shunt. So beraber tekrar bakalım. Input is voltage, output is voltage. What kind of amplifier is this?
Voltage.
Voltage amplifier.
This is voltage amplifier. How about the feedback? Is it a voltage current feedback? Is it a voltage feedback?
Voltage.
Is it a voltage feedback? So what kind of amplifier is this?
Current.
Output is current, input is current. Okay. And this one?
Voltage current.
Okay. So input is voltage, output is current, and this one is current voltage. Okay. So why do they say series shunt? Because when the output is voltage, we always take voltage as shunt. And when the output is voltage, the output of the feedback is voltage, we always have to do it in series. Okay. So this shows the feedback structure. Series shunt. You connect the voltage in series. You sense the voltage in shunt. Okay. Mesela burada shunt series demiş. Feedback structure current olduğu için current'ı seri bağlayamazsın bir network'e. Değil mi? Çünkü toplayamazsın akımları. Current shunt bağlamak zorundasın. Output'ta akımı da feedback network sense edebilmek için seri olarak almak zorunda. Şu akımı sense etmek istiyorsunuz. Nasıl alırsınız? Seriyi buraya bağlarsınız. Okay? So it's series. So şurası kısacası series shunt series shows these connections. For instance, shunt. As you can see, is connected shunt because we are summing the current 1, current 2. They are connected in shunt. Okay? Voltage voltajı sense edebilmek için voltmeter gibi düşünün. Şundaki voltajı sense etmek istiyoruz. Ne yaparız? Buraya bir voltmeter bağlarız. Değil mi? Şu ve şu. Same logic. You take the voltage and sense it using shunt connect. Dolayısıyla bunlar aslında feedback network'lerin isimleri. Bu şekilde söyleniyor. Series shunt feedback. Voltage feedback de diyebilirsiniz ama aslında bu da kullanılıyor. Okay. Bu devreleri de biraz kendiniz bakın. So we can discuss this more details. But as you can see, input is voltage, output is voltage. Here input is current, output is current. So the notations are important. For instance, here is also outputs, right? But the notation shows that we actually care about the current. That means you have to take the current, and that current, for instance, still is this current, and it should be connected to somehow input in a way that this is the feedback structure, in a way that it sums up with the input. Kolay değil dediğim gibi bunları anlaması. Yani bir devreye hani output, input nasıl feedback'i bağlayacağız vesaire kafanız karışabilir. Mesela şu devreye bakarsanız bu devreyle aynı. They are same circuits, right? But here we take the output and that voltage we connected through this network. But here we cannot take this signal, so we have to find a way to get that current actually to deploy it back to the input. So if you connect this from here, this feedback structure instead of this, then you wouldn't get any signal at the output. So yeah, as I mentioned, this will take time. Now there is another important chapter in this lecture, and that is called loading. So far, through the loading mechanism, we ignore this feedback structure actually loads this circuit. The impedance of this feedback structure, we ignored it, okay? Similarly in this one. So all these feedback structures actually have non-ideal impedances. This one, as well as output impedances. And they load the main feed-forward amplifier. So to actually solve the circuit well, we have some method, and this method, I summarize it here, is a step-by-step procedure to analyze feedback circuit. Okay, let's take a break, then we can go through this little bit further details. But you can look at these things in the break if you like. I'll leave this open. So the most important thing is to identify the topology. So at the input and at the output of the feedback or at the feed-forward amplifier, is it a voltage or is it a current?